All right, my end. I'm going to go ahead and go. All right, thank you guys. Thank you very much for coming by over here. If you hear some, I am a K-12 teacher at Charlotte Latin School. You might hear some rumbling in the background. That are students working on projects right now as we speak. We are our big claim to fame is we were doing STEM education back and starting in 1989, and then we were also first use Raspberry Pis, first to be in the Fab Foundations Fab Academy. What we do is we have a lot of kids. Every year we have students go in a very intense Fab Academy experience with Neil Gershenfeld, and we were the first high school to really do that on a consistent basis. So I'm going to make it quick because we don't have a lot of time. Um, I'm sharing what we've done with AI in terms of teaching microcontrollers. And this has really evolved very quickly in this last fall. So, real quick, so we all know, everybody in this conference know AI is an amazing tool. Like Archimedes, give me a place to stand and a lever and long enough, and I'll move the world. But I would also give you the other thing we as teachers worry about: artificial, the tools. Exactly, the tools are the subtlest of traps. From Neil Gaiman's The Sandman. And I think we all get worried about over reliance on a tool. You look at this car stuck on here. This looks what my own children and my students uh, using a GPS at some point. They stop thinking and they just use the tool, and then they're relying on the tool. And then as we talk about this, I wanted an experience that was much more. Let's not use AI like this. Take a single bulletin point, make a long email that looks like you wrote, and someone else takes email, takes your long email, and then takes AI to shrink it back down. And we're just, spin it. Let's not use AI to create more work and not really get any farther, any quicker. So, what I won't be talking about is prompting or computer vision. Those deserve almost their own classes on prompting and computer vision. There's a lot of people doing that, so I'll leave it to experts there. What I will be talking about is technical concepts. Just an example what you could use in a science or a STEM class using AI, for example, explaining technical concepts, a real quick, easy method you may or not already be doing. All right. So how do we it's 3:29 right now. How do we teach and then how we teach microcontrollers? So explaining technical concepts, think of it this way. When I get a concept, our curriculum changes 30% a year because just the technology keeps changing. We started back in the day with Arduinos, now we're doing the ESP32s, 10 times faster, it does a lot more things. Well, when I'm explaining technical concepts, even when I'm getting started, I'll start with, say, a pull down resistor. Why do you need a pull down resistor? Well, explain the technical concept if I'm 12. Then, once I understand that, explain it to me as if I'm 18. And if I need to, explain it to me as if I'm an electrical engineer. So up here's a perfect example. Explain a pull down resistor as if I'm 12 years old. So imagine a light switch. You're telling the sixth grader, and they can read this. You can either give it, make it a PowerPoint, or explain it yourself, but explain it where a sixth grader can understand it, and then explain how it works. Then, once you understand that, go on and explain it to them as if they're an 18-year-old. Because if they don't understand it at the most basic level and generalities, they're not going to get it at this level necessarily. I think most people would not. So we're doing that right now and having a lot of success. I also think it's a good strategy for all the teachers in here. When you get the student, I don't understand it. Well, wait a minute. What do you mean you don't understand it? Do you understand the written word here? So I used to say, break it down. Show me at what point you don't understand. This kind of addresses that same thing. Well, okay, explain it to you as a high school age. Let's go a little bit younger. There's nothing wrong with that. Let's go with simple. Um, and then you can see that goes through that. So that would be one tip today. If you're not already doing it, think about doing that. I think you're going to find a lot of success for your students and honestly for yourself at times. Now, the next thing is a basic premise. Do you remember any of the details of the test you took when you were 14 years old? I'm willing to bet to say you didn't. But I bet you remember that school project that you did.
Mm-hmm.
That's what you remember, the school's project. So the idea there is learn. So if you really think about STEM, STEM is applied math and science, project-based. But the key is it's got to be both, it needs to be rigorous. So in perfect examples, when Neil Gershenfeld of MIT says, blinking a LED in a lab can be life-changing. Like, oh my gosh, this is so cool. Now I'm interested. I want to learn more. So what AI, we've been finding this fall, it helps students see success quicker, which causes them to want to learn more or add features, which in this instance is positive project creep. I want the kids to build something, then go home and keep adding to it. So how do we do this? Oh, but I want to make this point. This does not mean we're making the class less rigorous. Actually, we're making it more rigorous because now we can expect more from our students. And so this is not, hey, they throw AI out there, gives them an answer. Okay, AI can tell me how to blink an LED. So this is more of this. Also, this method teaches them troubleshooting. I can't say enough how much that'll help you as an instructor. Their ability to troubleshoot is first a really important skill that they really need to leave school with, but it also allows you to have more time to work with kids on more difficult problems. So in other words, they haven't plugged their microcontroller in, and this is an agnostic. It can be an Arduino, ESP32, Raspberry Pi. It doesn't matter what I know Raspberry Pi is not a microcontroller, but you're getting my point, I think. So let me, for example, see this RC car on the left? It's the size of a little Hot Wheel. See that table on the right side? This thing, it's a walking table. We saw it online. Kids are coming after school. They just want to build this. This is not even part of the Fab Academy. These are kids that are interested in making it. The RC car, I guess we did do in electrical engineering. Well, with AI, we're able to build that thing much faster. So let me give you a basic. On something, make sure it blinks an LED, make sure it does hello world. And so we use WalkU, but other people could use Tinkercad. Install the Arduino software, connect to it. Teacher, you probably installed the software. But in this case, we're using an ESP32 board. We see if we can blink the LED. Now, what we do is we have this troubleshooting guide, and we have the kids work their way through it if it doesn't work. In this case, it was with sixth graders, so we have a Tinkercad simulation. So we have them simulate it once in Tinkercad. Do you have the pinouts? What not? And then we know when they get done, they got the LED blinking. All right, great. So you've got one component. So imagine you had a workflow. You can, this is what we did with electric car. That radio, if you think about the remote control, it had to have a servo and it had to have LEDs. So we got the LED portion, boom, done. We can make the lights. We do it again. This time, all we do is worrying about doing the servo. Now, what's great about this too is you use the example libraries. All boards come with example libraries, and all example libraries, almost all of them have some kind of hello world for that particular sensor or output. It's important because now we're getting examples of software that we know work. If it doesn't work, we know it's our hardware. We fix that. The AI is going to have a harder time with hardware that's outside the computer that you can't really check. So I get my servo now to run this RC car. I've got that. So now I have control the lights on the car, servo on the car. Then I get a motor shield example. Again, if I have to install a library, the kids do that. Plenty of examples for these. So I have 3 different components, all separate. And in this case, we added a camera, which might be even overkill. But we set up a camera, and that one's done separately. Each one of these phases, the LED, the camera, the servo, the motor are all done separately. Then what we do now, so we've tested each component. We know the hardware is hooked up properly for the LED, the servo, the motor, the camera. The code works for each component. We got to the servo. If it didn't work, you don't go to the next step until you get that servo to work. But using examples, having plenty of things to show you how to hook it up, we have pretty good success right off the bat on those. We have 4 different objects here. We have code examples that work. This is when AI is cool. So we're going to use AI to combine the 4 components to create a web server that controls our remote control car. So we're going to add 2 components at a time and just we'll combine it. So for example, get the LED and you say with the servo, I want the LED to go on and the servo to go on and control it with my on the web client. So I've got a web client. I tell the web client to say, combine the web client software with that LED. I now control with that web client the LED. Then I take that software and combine it with the motor, with the servo, with the motor. Just systematically add the components. You're going from simple elegance. I really don't like KISS. I think you need to. We stress elegance is very simple, and then you add complexity, and it really works well. So because the AI is using all code that already works. You've already proven that. So it's easy for the AI to combine it. So we did that whole thing with some students. We did that in 90 minutes, write all the code for that. I would have taken us a week and a half. And now we go back, we have AIs give an explanation, which you as a teacher make sure to go through it, but explains all the different parts of these codes. And I'm kind of speeding through this quickly. As we go to each thing, like in the servo motor, I might say to the kids, change the change the blinking on the light, change the servo. So you know your examples are actually working. And then you end up with, for example, that RC car. Today, another example of this, before I go on, if I can set that hook, I get students to do amazing things. Early success is important to help set that hook. Getting that all the program and not struggling for 2 weeks just to get the servo to work, I think is a game changer. And we're seeing it in class. Also, this technique is building really good engineering principles. You start off simple, you test components before you go on, you put in everything together. All right. And then at the end of this, you can have higher expectations. So what we really got to go through this as teachers is then say, okay, sit down with them and start talking to them about, well, what is this code doing? Can you, on that web server, can you tell it to move the button over? Showing them how to look on the code and see what things they're changing. And then if I've got them this stoked, they're going to want to go ahead and do it at home. All right. And obviously, it's obvious they have to be able to modify code AI without in your presence. So you have that. I will give you one more thing. We'll have time for questions. We just did, and here's where it's really kind of cool and getting exciting. We're doing in a bioengineering class, they're doing kinetics, and we're using cameras to study the acceleration as they move. And a teacher said, hey, I found this lab. You can do this. She goes, too bad we don't have accelerometers. And I started thinking about, well, we do have accelerometers. We have to do ASPS32. We were able to build a portable accelerometer that measures their movement, that uploads to their phone. And that was a couple-hour project done. That would have been a Fab Academy project a few years ago. So I went really fast. Do you have any questions?
Feel free to ask any questions. This was probably unexpected and outstanding.
I may have missed it at the beginning, but what age group are you working with here?
I could do this with middle school. I could do this with anybody you're teaching robots with. Now some of this stuff is highly technical. It would definitely spiral up. But yeah. I would teach middle schoolers and 4th and 5th. I teach robotics to 2nd and 3rd graders. But I would tell you this troubleshoot. The cool thing about doing it this way, if I can get my screen back up. All right. What I can tell you what's cool about this, it's really hardware agnostic and software agnostic because it's just really a system here. Right? Let me stop sharing your screen so you guys don't have that. Okay. So what it does is it gives you the examples that are already there. So the AI is going to be much more accurate when you do it. But even if you're not letting your kids use AI, you're still doing troubleshooting in a very process. Here's what we do. Everybody, not just kids, everybody wants to take their robot and have the finished robot. They want this. This is what I want right now. They want to build the whole train finished, ready to go, right?
Right.
And that's not how it works. If you're designing a train or anything, that's complicated. So we've done this. We do like with sumo bots. How I would do with sumo bots, I would start off whatever you're going to be your hello world version of sumo bots, depending on what you want to do. You could have, I want the robot to go forward. All right, you teach them motors on that, get them working on that. Then you say, it'd be great on my sumo bot to read the values that the robot's sensors are getting. So I would teach them then the sensors. Then I would teach and have them test that, and then use the AI if you can use AI, or combine it after that. That makes sense. But then, as far as getting into microcontrollers and what we're doing with ESP32s and all that stuff, we're doing it with freshmen. We'll be doing this with everybody.
It makes a lot of sense.
Yeah, I'm teaching some summer camp electronic maker, and I don't use AI with the kids, but I do use AI for myself to keep ahead of the kids.
Oh, absolutely. Absolutely. But as you're getting prepared, now you can start thinking about your AI camp.
Yeah.
Okay, I got the robot working. Go get a cloud server example. Like C does really good stuff with their ESP32. Get that example, then pretty soon they can be controlling the robots with your phone. And that really is kind of powerful. And we at our program, I say this modestly, we have a lot of success with our kids and how they're doing in their future pursuits. I think this will be
where's your program, Tom?
It's in Charlotte. It's Charlotte Latin School. We're a K-12. We're a Fab Academy school.
Charlotte, okay.
So where are you located?
Pittsburgh. I'm at the Carnegie Science Center Fab Lab.
Oh, yes. And I know Liz was from Carnegie.
Yeah, she came out of Carnegie. She's actually sitting in my lab right now, and I'm sitting at home because she didn't have electricity this morning.
Okay, good. Good. Well, Carnegie does so much great training on robots and things, be it vector or whatever those were. So we do a lot. We still do sumo bots because we don't. We can use existing robots, and
we're using Arduinos and a bunch of different robots. But yeah, it's
we've gone. I'm moving more and more to ESP32s or into Picos as they get.
Yeah, I am personally too. Personally, but not in the lab yet.
There you go. Yep. Yep. Is anybody else doing something with microcontrollers and AI?
Personally, I'm an ICT teacher, and sometimes I need to understand how to teach some coding concepts. And I've tried your approach for me, and starting to develop my own knowledge of coding with microcontrollers. And AI has actually helped me speed up my learning process and completing projects. You've just shown me the logic next step. Take it to the students. For us teachers, AI can be daunting because we feel, now, what's my role as teacher if the AI teaches for me? But actually, it speeds up, and our role is exactly what you have just shown so well. Give them the spark, make them get interested.
It's we have kids here. If we didn't turn the lab off on Friday afternoons, we'd be coming out. They get into it and they're just rolling with it. Otherwise, we're open all the time. But by the end of the week, we're kind of wiped out.
That's the best that we can hope to achieve.
Yeah. There we go. Sadat, how are you doing? Well, how's your fab stuff? He's from Turkey, and his high school is going to try to do Fab Academy with this stuff. So how's that going?
Yes, it's perfect. We started with 5 students this year.
All right, good.
And adaptation time,
Right. Okay. Anybody? If nobody else, I don't want to hold people just to hold them. I'm happy to answer any questions.
We have 4 minutes until the end of the session.
I wanted to make sure I got through all of it. I can show you. So this is the ESP thing we did just today. So this is a perfect example of. Let me show my screen here.
Go ahead.
Let me show you right. Whoops. Let me share my screen. Here we go. All right. 4-minute warning. There we go.
Yes.
I got your
4
screen.
minutes is an eternity.
Yes, we'll get it right here. All right. All right, so here we go. Can you see my screen now?
Yes.
All right, so this, and in some of this, we did some things to speed it up. We're using Seed Studio. We make our own, mill our own boards. As our Fab Lab, we can make the boards, we can do it all. But when you're prototyping real quickly, you don't necessarily have to get out and start soldering right off the bat. So this went from a concept to an idea within a few hours. And so this is an ESP32 microcontroller. That's an antenna on it. Here's a basic accelerometer. Here's an OLED screen. So we said, hey, we want, here's a project. We're going to use these materials because we want something that can do it. We want something and we gave the design specs, but basically this is what we required. Because you want the OLED screen to see your data, make sure you're collecting data, but you want to be able to put it for data visualization. So we did, I explained boards and libraries because that's really important on this whole method, that you add the board and you have the right libraries for them. And then we showed them how to do that. Here's the 32.3. The reason we went from Arduino, we explained to kids, this is 10 times more powerful than this chip. This chip's $6 or $6 or $7. These are still legit ones are 18. We used an expansion board. So, and here's all the programs we did. Blink LED, they did to start it off. Hello World OLED. Then that's a 3-axis accelerometer. They made sure that was worked. The next programs tied the accelerometer to OLED screen. Then we made the web server. Then we added graphics to the web server. And then we made it so the web server would download the data. And that was in a bioengineering class. So that's what makes it kind of cool. And do I have some data here now?